Hello, class. My name is Brandon Lipscomb, and today we embark on an exploration of one of humanity's most significant scientific discoveries, the nature of light. For centuries, light has captivated scientists, lighting our environment and challenging the fundamental principles of physics. Is light a wave that moves through space, or a particle that travels in discrete packets? This question has sparked intense debates and groundbreaking research leading to a transformative understanding that transcends traditional physics. This journey begins with the early theories of Sir Isaac Newton, who speculated that light is made up of particles. In contrast, Thomas Young advocated for the wave theory of light. The advent of quantum mechanics introduced the concept of wave particle duality, demonstrating that light can exhibit both wave-like and particle-like behaviors, depending on how it's observed. As we dive into this topic, we will uncover the experiments and breakthroughs that have guided our understanding from Young's double-slit experiment to the pioneering work of Albert Einstein. The duality of light not only shapes our comprehension of the universe, but also continues to inspire scientific innovation and discovery today. Interestingly, I consulted a few chemical engineers in my workplace about their theories on light and received a mix of opinions, with some supporting Newton's particle theory and others leaning towards Thomas's wave concept. To begin, I believe it's essential to distinguish between waves and particles. According to Webster's dictionary, a wave is defined as a disturbance or variation that transfers energy progressively from point to point in a medium and that may take the form of elastic deformations or of a variation of pressure. Waves are often visually represented by water waves, which occur when an object like a stone is thrown into a body of water. Sound also travels as a wave through air, with air molecules oscillating in the direction of the wave's motion. When you clap your hands, you create a pressure disturbance in the air that propagates as sound waves, demonstrating that waves are patterns or disturbances moving through a medium. In contrast, a particle is described as a relatively small or the smallest discrete portion or amount of something. This definition implies that particles possess mass, which can be measured or weighed in some fashion. Many properties of light can easily be explained through a particle model. For instance, when light reflects off a smooth surface, the angle of incidence equals the angle of reflection, similar to how a basketball rebounds off a smooth surface. This observation aligns with Newton's view of light as a particle. Newton argued that sound, which was known to travel as a wave, could navigate crooked pipes and corners, while light could not, supporting his corpuscular theory of light. Albert Einstein shared similar views, proposing that while light sometimes behaves as a wave, it also consists of discrete energy packets known as quanta, now called photons. This concept was crucial for understanding the photoelectric effects and the behavior of light in general. While Newton and Einstein's particle theories of light represent different paradigms, they each have limitations that modern physics seek to address. At this time, both weren't completely wrong. Thomas Young challenged Newton's corpuscular theory through his famous double-slit experiment, demonstrating that light exhibits wave-like behaviors. Young theorized that if light were purely a particle, it would pass through a narrow opening without diffraction. Diffraction is the slight bending of light as it passes around the edge of an object. The amount of bending depends on the relative size of the wavelength of light to the size of the opening. If the opening is much larger than the light wavelength, the bend will be almost unnoticeable. However, if the two are closer in size or equal, the amount of bending is considerable and easily seen with the naked eye. Thomas Young conducted his double-slit experiment in 1801, using sunlight diffracted through a small slit to create coherent light, which then illuminated a screen with two slits. Young observed that when the slits were close together and small, distinct bands of color appeared due to the interference patterns, suggesting that light behaves like a wave. The only explanation for the pattern was that light was constructively and destructively interfering like a wave. Waves can interact with one another if they occupy the same space. When waves interact, they create a new wave called a resultant wave. The resultant wave is simply the addition of two or more waves, called the principle of superposition. This same wave behavior of constructive and destructive waves can be produced in water. This illustration helped me understand this phenomenon. However, a challenge remained for Young's theory. Waves typically require a medium to propagate, which raises questions about how we can see light from the sun and distant stars in a vacuum without the medium. This conundrum puzzled scientists and seemed to lend more credence to the particle theory of light. The breakthrough came with the work of Michael Faraday and James Clerk Maxwell. Faraday discovered that light possesses electromagnetic properties, and Maxwell formulated mathematical equations that supported Faraday's theories. Together, they demonstrated that electricity and magnetism are interconnected, revealing that light is a form of electromagnetic radiation that can travel through a vacuum without needing a medium. So, does this mean light is definitely a wave? Niels Bohr recognized the limitations of classical physics and expanded our understanding of atomic behavior. His research on electrons was drawn from emerging quantum theories established by pioneers like Max Planck and Einstein. Bohr explained that when matter emits light or heat, it does so in discrete packets of energy called photons, which possess specific properties such as speed, frequency, and wavelength. He clarified how electrons transition between energy levels by absorbing or emitting light. Photons embody the dual nature of light, behaving as both waves and particles. This discovery was fundamental to the development of quantum mechanics. Newton's belief in particle-like behavior stemmed from how light reflects off surfaces, while Young's experiments confirmed its wave-like properties. Ultimately, both sides of the debate were correct. The discovery of these great scientists have led to modern applications utilizing the understanding of light. For instance, fiber optic technology leverages the wave nature of light for high-speed data transmission, allowing light pulses to convey substantial information over long distances with minimal loss. Additionally, spectroscopy uses the wave nature of light to analyze materials as different wavelengths interact with substances in unique ways, enabling scientists to determine compositions and temperatures without direct sampling. In summary, the exploration of natural light reflects a rich history of scientific inquiry, showcasing how our understanding of fundamental concepts evolves over time. The journey to grasp the essence of light has not only shaped physics, but has also laid the groundwork for numerous technological advancements that continue to impact our world today. Thank you, and good luck on your scientific adventures.